Chemistry in the air. Today is International Hat Day. And we're celebrating with hats. HAT for short. And it's also Chemical Bonding Day Eve. So we're going to take a look at some bonding. Covalent bonding. We've gone through this already, but it's been a long weekend. God, it was a long. Looks like you just came back from Paris. I can tell by your hat. And you from Moscow. I can tell from your hat. And you from Texas. I can tell from your hat. You probably more like, where's that hat from? Arizona?
Yeah, Arizona, New Mexico.
Perth, Australia. There we are. We can just tell by the hat. You can tell a lot about a person. Kangaroo. Have some Roo burgers. Nice thing about Roo burgers is that little pocket. You know, the marsupial burgers all have those pockets where you just put the cheese inside, right? That you've got to be careful when you butcher a kangaroo, though, so you don't ruin the pocket. You just shrink it down to the burger. Anyways, covalent bonding is between non-metals, and these bonds are where you cooperate in valence electrons, where you're sharing valence electrons. And we went through this a little bit already. What we need to remember, though, is that electronegativity increases from left to right on the periodic. You have to know which one's the most electronegative. If you remember that fluorine is the most electronegative element, you can see left to right, it's always going towards fluorine. Going up a column or a family, fluorine. Now, you guys have this on your handout, don't you? Yeah? Yeah. Okay, 7 years I've done. These are electronegativities of the elements listed numerically. I won't be giving you this on test because you don't need that much detail, but just to show you. We leave the noble gases out. We don't have this. But fluorine being the most electronegative, okay, 4. See how it's increasing from left to right. It's increasing as you go up the column. There are some exceptions, and you can look around and see some, like right here, for example, there's some exceptions. But it's generally increasing from left to right. Okay? So the one thing you have to remember, and you might even just somehow remember, hydrogen was looking like too much. Hydrogen is kind of in between boron and carbon. Now, it isn't actually in the row, but you want to know where its electronegativity is, because hydrogen bonds a lot. So it's just slightly less than carbon. Less. Okay. Other than that, there's not much you need to memorize. You can always think of fluorine. I'm not going to try to fool you and give you something that's an exception. Out of your gallery. Okay. Now, flip to this. When there's unequal sharing of electrons between two non-metals, and I put this in tiny writing between decimal change at 1.6 apart. I put in tiny though because I'm not going to get you to count it. The atoms take on a partial charge. Okay? Not a true charge like an ion. Hydrogen and chlorine. Now, you take a look at it. They are two non-metals. Remember how I said hydrogen is sort of in between carbon and stuff? Carbon and boron. Chlorine is basically, I'll pull down this periodic table, right underneath fluorine. So you know that it's going to be close to fluorine, it's going to be more electronegative without considering even though they're different. Chlorine's more electronegative. It'll have a greater attraction to the electrons. It gain a slight negative charge. The hydrogen will have a slightly positive charge. We call this a dipole. And how do we indicate dipoles? I use this method here. I'm just tracing over. I put sort of like this. Here's how I think of this. I put the plus sign on the positive end, then I make an arrow saying the electrons go this direction. That's what that's a this is. Okay? Another way, though, to show dipoles is to say that's a small letter D in Greek alphabet called delta. So delta means change, you know, like in math, use a capital letter D with a triangle. That's delta. This is small delta. And you just think of it as a partial charge, a partial negative charge, a partial positive charge. Some people think it's kind of unique. Anyway, kind of a fancy key. You can indicate it that way. Use one method or the other. I don't care which one. I tend to use the other. Yes.
So we only have to do that.
Yeah. Typically, though, you're going to, I think we're all playing. Most people settle on this. But you might see the other one be on top. And I might throw that. I might use them in combination like this. A bond with a dipole is called a polar covalent bond, or just a polar bond. And water is the best example. You look at water, oxygen, remember how we said hydrogen would fit in between B and C? So oxygen is way closer to it. It is quite electronegative. It's the second most electronegative element of it. And there's a strong attraction. Now in green, I have this dipole, I have this dipole. These are like vectors, they are. And in physics, when some of you do physics, just think of this. Two people are pushing on an object this direction, this direction. What's the net push? Well, that's what we're calling the net dipole. Okay? You've got to use your imagination a bit. And it's not like physics where I would actually get you to calculate the exact angle. Just a rough calculation. And I want to see net dipole. Now, I'm pretty certain who has to get the biology. You talked about polar bonds, right? You guys are taking polar bonds with other things. Yeah, I trust you. I know you. Probably did.
Absolutely.
Okay, I'm sorry. I'm stopping myself. We have this topic. I don't feel
You
like
have
that.
a thought.
Right. But I am stopping myself. I know you don't, but I do. Okay. So water is important. Actually, we'll get back to that a little later on. Ionic bonds. When there's a difference of electronegativities that is large, 1.7 or larger mathematically is sometimes used, but basically if it's metal and a non-metal, then we consider the electron from the less electronegative atom removed and transferred to the other atom in the bond. In general, ionic bonds form between metals and non-metals. So I don't need you to calculate that difference or something. Sometimes it doesn't quite work out. The metals lose electrons, they form cations. And since the non-metals are more electronegative, they gain electrons. They're anions. Okay. That's an actual transfer of electrons, not a covalent bond, an ionic bond. They're actually strong. The 3D arrangement of cations and anions is called a crystal lattice. Now, I drew one of the simplest ones. There's other ones. This is a cubic structure. If you can imagine, is going on forever, right? So, negative, that's the chlorine. The positive, it's the sodium. There's one behind it, in front of it, like it goes out in 3D over and over again. When you look at crystal structures under a microscope, you tell the difference between that and sugar without tasting. The crystal structure of this, it'll be real sharp edges. Crystal lattices can go on indefinitely. You'd never find a sodium chloride molecule like you would of a water. They don't exist. Instead, it's just a repeating pattern of NaCl ions. Okay? Did you guys ever look at these under microscopes in grade 9? Yes? No. Or you just sort of balk and you're not saying yes? I'll bring some out then. Okay? Just so you can see that. And while I'm bringing them out, here's what you guys are going to do. Intermolecular forces are the forces that are present within compounds. Ionic bonds or covalent bonds. Now, first of all, we're going to contrast this word with intramolecular and intermolecular. Now, intra is the word you're not, the prefix you're not as familiar with. So there's going to be intermolecular later on. So I'll ask you this. You know the word inter. Let's just think about it. What is an international flight? Between two different countries. So inter molecular, I-N-T-E-R, not this one, means between molecules. Intra, inside. So I want you to know within the compound, inside the molecule. It's there, but I mean, I'm just picking words. And the two types we're figuring out, we're just limiting to either ionically bonded or covalent. So there's other things, but we're not getting it. So I want you to take a look at this. Basically, ask yourself, if there's a metal and a non-metal, it's ionic. Otherwise, it's non-metal, non-metal, covalent. Okay. So you guys do these while I get out the compound microscope, hopefully. Oh, gosh. No, it's already copied with it, right? Is that right? Yeah. Okay. You guys doing that? I'm pausing the video and getting out the crystals. You had a chance to look at the atoms, but you also had a chance to look at the salt under the stereo microscope, right? At the same time, I was hoping you did this, right? Ionic or covalent bonds and why? So H2, H hydrogen, is it a metal? No. And it's obviously a non-metal with a non-metal, right? So it is covalent. And that's as simple as it gets. Non-metal. Strontium and bromine. Ionic because it's a metal with a non-metal. Cation and anion is actually a better answer. You'll see there's 99% of what you do, though, with me is going to be metal and non-metal. There's going to be some. Okay, NO3. Pardon me. Oh. Oxygen and nitrogen are non-metal, so hopefully what? Non-metals for HBr. Uber. Over. Whatever. The last one, what did you guys put down for ammonium chloride? Why did you do that? Because you're correct. Not a metal and a non-metal, though. It is a cation with an anion. Exactly. Not metal and non-metal. There's two types in this one. You can think of this as ammonium chloride, but then sometimes some years people would say, what about just the actual ammonium ion? Within that, there's covalent bonds, the ammonium ion. But I wasn't looking for that. I'm not going to try to show you. Okay. Okay. Now we're back with intermolecular forces. And like I was saying, international travel between countries, right? International news between, outside of Canada and stuff. Intermolecular forces occur between molecules, between two different molecules. Hydrogen bonds, polar forces, London forces. I think you're familiar with hydrogen bonding, the idea of it from biology, correct? Well, maybe somebody wasn't there. You probably talked about polar forces and stuff. This is where I said we're going to revisit water and stuff. Well, it'll come up. Okay. So, polar molecules. A molecule may have polar covalent bonds inside it, but the forces might cancel each other out. And this is where we have to know that geometry we were looking at last week. This would be considered a non-polar molecule, even though it has polar bonds inside. However, if the forces add up to a net dipole, you have a polar molecule. So, are the following molecules polar or non-polar? Now, look at these five. Starting with the first one, that's a great place to start. We're going to draw them. This is why we've worked on this last week, and we're going to draw them in 3D, if necessary. Oxygen isn't necessary to draw in 3D. Oxygen. It has a double bond. You guys know how you figure these things, right? Better. Okay. When I look at oxygen, I really didn't even need to draw it out, actually, because which is more electronegative, the oxygen on the left or the oxygen on the right? Which one has You go to the polar electrons. Neither. They're the same. So it's an equal tug of war. There's no polarity difference there. No, it's not a polar bond. So that one is not polar because it's equal sharing. It's a perfect 100% covalent bond. So I'm going to just say not at not polar. Since it is a 100% covalent, you can't get more equal than the same thing. All right, CO2 though. You remember our structure for CO2? Maybe you do, maybe you don't. So carbon wants to bond 4 times. Oxygen wants to bond twice. You remember how this one works? Yeah? Two double bonds, and they're in a straight line. Because these two bonds, I think about the central atom. The furthest they can be from each other is 180. You know, one point north, one south. Okay. Now within this bond, there is a definite difference between carbon and oxygen. Which one's more electronegative? Oxygen. It's right next to fluorine. So closer. So what you're going to do is, I'll do mine above. I say the positive end on this bond is above the fluorine or above the carbon, and the electrons are attracted towards the oxygen. Likewise. Okay. And that is a linear molecule. That's why we hate molecular. So if you have an equal, because it's a CO bond on the left, CO bond on the right, so the equal bond, and you have a tug of war, what happens there? Does anybody win? Not this. So this is a different reason. It's not a polar molecule. But the reason is, since the polar covalent bonds cancel each other out. So it has polar bonds, but they cancel each other out, so it's not a polar bond. Okay. On boron is this one I told you guys about. It's kind of an exception to most of these. Most things want a grand total of 8 electrons. Boron only wants 3 bonds, 6 electrons. And when it has no spares left over, so I'm going to draw this one. Diagonal planar. What we call the geometry. Okay. When I see this, I shouldn't have to even think about it. So fluorine is the most electronegative thing on the periodic table. So negative. And therefore it pulls. So I'm going to say, well, it's a positive end here, pull. Positive end here, pull. The positive end here, the boron, pull. So the electrons are being pulled towards the fluorine to each of those 2 bonds. This is a 3-way kind, and it's symmetrical. So is there any end dipole force? No. Same as above. Like, yeah, they're all the same 3-way. It's the same reason, too. Not polar, since both of their covalent bonds have polar. I'll just copy. I'm no fool. All right. How about this carbon tetrachloride? What's the geometry of this? How would you draw this in 3D? Tetrahedral, yeah. I'm going to go with that. Carbon in the middle. I usually drew it like this, 109.5-ish. Right? I'm going to put the Cls with the electron. Okay. Out of these ones, which one's more electronegative? Just pick which one's closer. They're not in the same row, so we tend to do the left. But I think the carbon's far enough away that I can be pretty convinced that chlorine is more electronegative. So that means carbon will have a slight positive on each bond. We're going to draw them. Now that's a four-way tug of war in 3 dimensions. So once again, as before, same reason. A lot of polar molecules is the polar covalent bonds. Hot dog, is there any such thing as a polar molecule? Well, water is, but I don't have PCl. It is polar. We're going to figure this one out. P wants 3 bonds, it has a lone pair of electrons. So I'm going to go P in the middle. Then the bottom of that tetrahedral, out. Okay, let's think about this one. This is like a tripod, right? Now between P and Cl, they're in the third period, we call it, or row. Cl is definitely to the right of phosphorus. It's more electronegative. That means the arrow will go from positive end of P and the L is where it goes to. Now remember, this is a 3D shape. So I can get the model up real quick and double check your understanding. I'm going to do it like this, so just use the yellow ones like the colors. Do it quick. Geometry, really. I know this doesn't show up. Okay, this is like a tripod, right? Like triangle-based pyramid. So if there's a force coming down this direction, this direction, this direction, like 3 forces pulling, not sideways but down at the same time, it would be like if I gave a day on a rope, I a rope can be attached to that, and the rope pulled kind of at that angle, this angle my arms are. It would start to come down a bit, wouldn't it? Does that make sense? So the net dipole, what I just drew, got my mental pen again. I'm going to just push mine up a bit because it came. This one has a net dipole for sure. And here's what we do. We don't need to draw the net dipole over top of anything. The vector, you can move it wherever. So I tend to just put it in a clear open space. And I call it net dipole. I'm always looking for this if you have a polar. So indicate the net dipole, and it's a polar. Okay. The four molecules are attracted to each other due to their positive and negative net diet. Good. Good. I'm going to ask a question. However, would you guys like to have a little break from this and start on your assignment a little bit? I think it's a lot of